In this unit, we are looking at positive term series, infinite series that is, and we are trying to determine whether they converge or diverge. If you've been watching, we just looked at some observational methods for determining whether a series converges or diverges. For the rest of the lesson, we're going to look at some formal investigations to determine if a series converges or diverges. We will be looking at the integral test, the direct comparison test, the limit comparison test, and one of my faves, the ratio test. The ratio test is actually for another lesson in this unit. This particular lesson will finish with the limit comparison test. So the limit comparison test is actually a test whose logic you should already know from the previous unit. Same with the direct comparison test, and kind of the same with the integral test. Simply, if the integral of the corresponding function converges, then we would say that the series converges. Likewise, if the integral of the corresponding function diverges, we would say that the series diverges. So let's take a look at several examples. Example number 1. This is a very important example. This particular series has a name. That's how important it is. It's called the harmonic series. You don't want to say the harmonic series, you want to say the harmonic series. And we're going to investigate with several methods whether or not this harmonic series converges or diverges. Let's take a look at an observational test. Suppose I decided to employ the nth term test, and I took the limit as n goes to infinity of the nth term, and that came out to be 0. Do you remember what this tells us? It tells us absolutely nothing. If the limit of the nth term goes to 0, it passes the nth term test, which only tells us that further investigation is required. It makes me sad to get anything inconclusive. So let's take a look at another observation. Well, I can say that this thing will diverge. This is the first thing we did. This is the second observational thing. Diverges as a P series. You see that? This is a P series where P equals 1, and that gives us reason for the fact that the series will diverge. So that tells us that the harmonic series diverges. So I'm going to add another little bullet here. We could have said right from the beginning, we could have said that the series diverges as the harmonic series. So we can commit that to memory that anytime we see the harmonic series, we can simply state it diverges as the harmonic series. So all three of these were observational, the third one being something that we memorize. So in part B, I want to do a formal investigation. The investigation I want to use here is the integral test. See, the integral test actually proves the P-series test. And I want to walk you through this. Okay, so in the integral test, the first thing we do is state, because it's formal, I want to be real formal about it. We state the nth term, which is 1 over n. The next thing we do is let f of x, so this is the corresponding function, be 1 over x. The next thing we do is we investigate the integral from 1 to infinity of the function f of x. So that becomes the integral from 1 to infinity of 1 over x dx. Now we go through and actually evaluate the integral. This is a limit statement. The limit as b goes to infinity, well, let's make sure that looks like an infinity, 1 to b, 1 over x dx, which equals the limit as b goes to infinity. We have our antiderivative, natural log of absolute value of x. The absolute value is not needed as we go from 1 to infinity. It's all positive, but I'll put it in anyway. 1 to b. So this becomes the limit as b goes to infinity, the natural log of b minus the natural log of 1. Well, the natural log of 1 is 0, and the limit as b goes to infinity of the natural log of b, well, that grows without bound. So this approaches infinity. That integral diverges, which will tell us that the series also diverges. So let's finish this out by saying, therefore, the sum from 1 to infinity of an, notice in the formal test I do a lot more notation, the series from 1 to infinity of 1 over n diverges also by the integral test, QED. For example 2, the sum from 1 to infinity of n times e to the negative n squared, I would like you to please use the integral test, the formal integral test, to determine whether or not the series converges or diverges. Please press pause now, and when you unpause, you will see the solution. So I'm led up to this point. The limit is b goes to infinity. So b is going to infinity, so e to the negative b, that's going to make this go to 0. It's going to make the whole limit then go to e to the negative 1 over 2, or simply 1 over 2e. So we would say here that the integral converges to 1 over 2e. It does not mean that the series converges to 1 over 2e. It does mean that the series converges. And just in case you had a little trouble with the integration, in pink I have drawn the u substitution needed to make the integration happen. Example 3, the series from 1 to infinity, 1 over 2 plus 5 to the n. We're going to prove whether this converges or diverges using the formal direct comparison test, whose logic is exactly what was described in the Chapter 8, the unit right before this. There are some key notational differences. an equals 1 over 2 plus 5 to the n, where before we would say f of x and then g of x, here we're going to say an and some nth term bn, and bn is going to be 1 over 5 to the n. Okay, so let's take a look at this. an and bn are positive, continuous, and decreasing. So I added the word decreasing, and I want to say on 1, 2, 3, ... because that is the domain of n. Not 1 to infinity including, but 1, 2, 3, those integers. In step 2, we're going to say that the sum from 1 to infinity of bn, the one that I chose, which is the sum from 1 to infinity of 1 over 5 to the n, does something. We should be able to tell by observation what this does. Maybe if I write it like this, you can see it a little more clearly. What if I wrote 1 over 5 to the n? Then hopefully you can say that this converges observationally because it's geometric with b1, the first term being 1/5, and the common ratio being 1/5, which is less than 1. Step 3, do you recall what to do here for the direct comparison test? We want to say an, which is this. We want to show that it's always less than or equal to the bn, 1 over 5 to the n. So since an is always less than bn, and the series for bn converges, or 1, 2, 3, we would conclude that the sum from 1 to infinity of an, which is the series from 1 to infinity, 1 over 2 plus 5 to the n, converges also by the direct comparison test. Number 4, the series from 2 to infinity, 3 over square root of n minus 1. Please prove whether this converges or diverges using the direct comparison test, pressing pause before revealing the solution. Solution revealed. One of the things that you may have missed, it starts with a 2 here. Since the series starts with a 2, I would say from 2, 3, 4, so on and so forth. And I'll repeat that here. So this series diverges by the direct comparison test because I chose a Bn and the sum of Bn is a P series.